Look around and you'll find steel almost everywhere. It forms the skeletons of buildings, the frames of machines, the bodies of vehicles, and the structures that connect modern life. But steel itself isn't mined from the ground. Before it becomes a beam, a plate, or a coil, its main ingredient begins as iron-bearing rock. Iron ore contains valuable iron minerals mixed with unwanted rock. The first challenge is to concentrate the material that will eventually become iron. The concentrated material is still not ready for a furnace. It has to be prepared into a form that can move efficiently through the intense conditions inside a blast furnace. These pellets are easier to handle and allow gases to move through the furnace burden, helping the chemical reactions happen more efficiently. Now the prepared iron-bearing material is ready for the machine. That will begin one of the most important transformations in steelmaking, the blast furnace. Deep below, enormous quantities of hot air enter the furnace. The temperature rises dramatically as the fuel reacts with oxygen. The rising gases react with the iron oxides in the ore, gradually removing oxygen and leaving behind metallic iron. As the material moves deeper into the furnace, the temperature becomes high enough for the reduced iron to melt and collect at the bottom. At the bottom of the furnace, the first major transformation is complete. Rock has become molten iron, but it still isn't steel. Freshly mined iron ore can arrive as large pieces of rock. Before a furnace can use it efficiently, those pieces have to be broken down into a much more manageable size. Crushing produces pieces of different sizes. The next step is to separate them because the furnace needs a controlled and predictable material feed. Some ore still contains iron locked inside the surrounding rock. To release more of it, the material can be ground into much finer particles. Once the ore has been finely ground, the iron-rich particles can be separated from much of the unwanted material surrounding them. After separation, the concentrated ore is blended to create a more consistent feed. A blast furnace performs best when the material entering it has predictable properties. But finely ground ore has a problem. If it is charged directly into a blast furnace, tiny particles can restrict the flow of hot gases through the furnace. One solution is pelletizing. Fine iron ore is combined with carefully controlled moisture and additives, then rolled into small, nearly spherical pellets. These fresh pellets are still relatively fragile. They must be heated so their internal structure becomes strong enough to survive transportation and the intense conditions of the blast furnace. Now the material has the form needed for the next stage. The prepared pellets will be combined with other furnace materials and charged into the blast furnace. The ore has now been crushed, sized, concentrated, blended, and hardened into a form suitable for the furnace. The next step is where the real transformation begins. At the top of the blast furnace, carefully prepared materials are charged continuously. Iron ore, coke, and limestone enter from above and begin their long journey downward. Gravity slowly pulls the solid burden downward, but the gases inside the furnace are moving in the opposite direction, creating a continuous exchange between descending solids and rising gases. Near the bottom, the furnace receives a powerful blast of preheated air through openings called tuyères. This is where the furnace becomes extremely hot. The oxygen in that hot air reacts rapidly with coke. The reaction releases enormous amounts of heat, and produces the gases that drive the chemistry higher in the furnace. The hot gases produced near the bottom now rise through the furnace, transferring heat and participating in the chemical reactions that gradually transform the ore. As the ore moves downward, its iron oxides react with the rising gases. Oxygen is progressively removed, leaving a greater concentration of metallic iron behind. Deeper inside the furnace, temperatures become progressively higher. The material passes through different thermal and chemical zones as it approaches the hearth. Eventually, the reduced iron reaches temperatures high enough to melt. Liquid iron begins flowing downward through the furnace toward the hearth. At the bottom of the furnace, molten iron collects in the hearth. Above it, the remaining gases continue their upward journey while the liquid metal waits to be tapped. The blast furnace has completed its main job. Iron ore has been reduced and melted into hot metal, but this material still contains too much carbon and other elements to be called steel. The molten iron leaving the blast furnace is called hot metal. It is already liquid, but its chemistry is still far from the composition required for steel. A torpedo-shaped vessel carries the hot metal away from the furnace while keeping it contained and hot enough for the next stage. Before the main steel-making vessel, the hot metal can be treated to remove some unwanted elements and prepare its chemistry for the next operation. The prepared hot metal is then charged into the basic oxygen furnace, where the chemistry of the iron changes dramatically. Along with hot metal, steel scrap can be added to the furnace. The scrap becomes part of the new batch and also absorbs some of the enormous heat released during refining. Now the most important refining tool enters the furnace, a water-cooled oxygen lance. A powerful stream of oxygen strikes the molten bath. The oxygen reacts with elements dissolved in the hot metal, releasing intense heat and driving the refining reactions. One of the most important reactions is the oxidation of carbon. Carbon combines with oxygen and leaves the molten metal primarily as carbon monoxide and carbon dioxide gases. At the surface, oxidized impurities combine with added fluxes to form slag. This floating layer helps capture unwanted elements while the refined metal remains below it. As oxygen continues refining the bath, the carbon content falls toward the required range. The material that began as blast furnace hot metal is now molten steel. The newly refined steel is still a liquid, glowing at temperatures far above the melting point of steel. Now it has to be transferred into a machine that can turn that liquid into a continuous solid shape. At the bottom of the ladle, a controlled outlet is opened. Molten steel begins flowing downward into a smaller vessel called the tundish. The tundish acts as an intermediate reservoir. It keeps the flow of steel steady and allows the casting machine to receive a controlled stream instead of relying directly on the large ladle. From the tundish, the steel passes through a submerged entry nozzle. The nozzle directs the liquid below the surface of the mold, reducing turbulence and exposure to air. The liquid steel now enters a water-cooled copper mold. The mold doesn't freeze the entire stream at once. Instead, it rapidly removes heat from the outer surface and creates the first solid shell. As the strand leaves the mold, the solid shell becomes thicker. Heat continues moving from the liquid core through the solid steel and into the cooling system. Below the mold, powerful water sprays continue removing heat from the moving strand. The solid shell keeps growing as the liquid core shrinks. As cooling continues, the strand becomes strong enough to travel through the curved section of the caster. Rollers guide it from a vertical path toward a horizontal one. Once the strand has completely solidified, it can be divided into manageable slabs. A moving cutting system separates the continuous steel into individual sections. What began as liquid steel is now a solid slab with controlled dimensions, but this slab is only an intermediate product. Its final shape and properties will be created in the rolling mill. The newly cast slab is solid, but its journey is far from over. It now moves toward a reheating furnace, where its temperature will be carefully raised for the next stage. Inside the reheating furnace, controlled burners surround the slabs with intense heat. The goal isn't to melt the steel, but to heat it evenly throughout its thickness. Heat reaches the steel from its surface and gradually travels inward. Because the slab is thick, its center takes longer to reach the required temperature. The furnace is divided into heating zones, so the temperature can rise gradually rather than changing all at once. Near the end of the furnace is the soaking zone. Here, the surface and center temperatures move closer together before the slab enters the rolling mill. At the furnace exit, the slab has reached the temperature needed for hot rolling. It is still solid, but now its resistance to deformation is much lower. But heating steel and air creates another problem. Oxygen reacts with the hot surface and forms a layer of iron oxide called scale. Before the slab reaches the rolling stands, powerful water jets remove this loose oxide scale from the surface. Now the heated and descaled slab reaches the rolling mill. Here, enormous forces will begin squeezing it thinner and longer. With every controlled pass, the steel becomes thinner and longer. The massive slab is beginning to take the form of the product it will eventually become. The thick slab now enters the roughing mill, where enormous rolls begin removing its thickness in controlled stages. The rolls don't simply flatten the steel. They force the material to flow, reducing its thickness while increasing its length. One pass is not enough. The slab moves through several controlled passes, with each pass reducing the thickness further. Thickness isn't the only dimension being controlled. Vertical rolls can also act on the slab edges to manage its width. With every reduction in thickness, more of the steel's material flows forward. A massive slab can gradually become a long strip, stretching far beyond the original dimensions. After roughing, the steel enters a series of finishing stands. Here, the reductions become smaller and more carefully controlled. As the strip becomes thinner, its speed increases so the continuous material can move through the finishing mill without breaking the production flow. Rolling changes more than shape. It also affects temperature, so the process has to keep the steel within a carefully controlled thermal range. At the final stand, the strip reaches a carefully controlled thickness. The huge slab that entered the mill has become a long, continuous sheet of hot steel. After passing through the rolling mill, the steel is no longer a massive slab. It has become a long, continuous strip moving toward the cooling and coiling stages. The strip has just left the final rolling stand. It is thin, continuous, and moving rapidly, but it is still glowing with the heat of the rolling process. The first task is to bring the strip down from its rolling temperature in a controlled way. Too fast or too uneven, and the steel can develop unwanted properties. or shape problems. Cooling is carefully controlled along the length of the strip. The goal isn't simply to make the steel colder, but to reach the right temperature at the right point in the process. Sensors continuously monitor the strip as it travels. Temperature measurements help the system control the cooling process and maintain consistent conditions across the moving steel. As heat leaves the steel, its visible glow fades. What was once orange hot becomes a darker red strip ready for the final stage of the line. Once the strip reaches the required temperature, it approaches the downsoiler. The continuous sheet must now be guided into a tight spiral without damaging its surface. The leading edge wraps around the rotating mandrel. From this point onward, every new section of strip is wound directly around the previous layer. Layer by layer, the coil grows. A strip that stretched across the entire rolling line is gradually transformed into a compact cylindrical package. Eventually, the strip reaches its required length. The continuous feed is stopped, and the newly formed coil is ready to leave the coiler. In just one continuous process, a massive solid slab has become a long, thin steel strip and then a compact coil. But before this steel reaches customers, it still has to be inspected, finished, and prepared for its final application. The finished coil now enters the finishing section, where its dimensions, surface, and material properties are checked and refined before shipment. To inspect and process the material, the coil is gradually unwound into a continuous strip once again. The exposed surface can now be inspected continuously for scratches, scale, cracks, pits, or other defects that could affect the final product. Thickness is measured continuously because even a small variation can matter when the steel is later formed into precision components. The system also checks the strip's width, ensuring that the edges remain within precise dimensional limits along its entire length. After being rolled and coiled, the strip can retain small amounts of curvature or shape variation. Leveling rolls straighten the material and improve its flatness. When customers need narrower strips, the wide sheet can be divided longitudinally into several narrower coils. Other applications require individual sheets instead of continuous strip. In that case, the material can be cut into precise lengths. Before the steel leaves the factory, samples and continuous measurements are used to verify that the material meets its required specifications. Once the measurements confirm that the steel meets its specifications, the material is approved for its next destination. What began as rock has become a carefully engineered industrial material. After passing inspection, the steel is no longer a raw material waiting to be transformed. It is now a controlled industrial product, ready for its next stage. Finished coils are stored according to their dimensions, grade, and destination, waiting to become components for another industry. Some applications need continuous coils. Others need individual sheets so the steel can be uncoiled, flattened, and cut into precise lengths. Other steel products are rolled into shapes designed to carry enormous loads, such as beams, channels, and structural sections. Flat steel can also be transformed into tubular products, where the sheet is gradually formed into a circular shape and joined along its length. Some of the steel eventually reaches automobile factories, where thin sheets are pressed into precise shapes for vehicle bodies and structural components. Much larger pieces of steel become structural frames, carrying loads through buildings, bridges, factories, and other infrastructure. And steel doesn't always appear as something massive. Smaller components made from steel operate inside machines, engines, tools, and countless mechanical systems. And now the entire journey can be seen as one continuous transformation. Rock becomes ore, ore becomes iron, iron becomes steel, and steel becomes the foundation of modern industry. What looks like an ordinary piece of steel is actually the final result of an enormous chain of engineering. From a piece of rock buried in the ground to the machines and structures around us, steel is one of the most carefully transformed materials on Earth.